Thank you for that generous introduction. I'm actually not a doctor. I just play when I work. No, actually, but I am pleased to be here. I am giving a talk that was originally designed by Tim Dennison, who was invited here to come. He was unable to come, and I found out a week ago. And said I'm happy to come out. I think it'd be very cool to see this conference and see what's going on. I've been very impressed. So a few disclosures first. This is a roadmap talk. It's technology that is not ready for prime time yet. We are, under investigational control. We do not have approvals for a lot of these things that you're going to see today. And I want to give thanks to all our collaborators that we have from around the world. We have quite a few in the US, including right here locally, which Rad mentioned. And want to thank them for allowing us to share some of their data. And also, Tim and I are both employees of Medtronic, and we have IP in some of these things that we're going to be talking about that. So that's my disclosure. So a lot of times, the Brain Initiative and other things related to that are likened to the space program. And we have this goal that everybody's joining to create and really do that. But it's so vast, as you can tell by all the talks that have been going on, that it's almost too much of a shot, really, to start. And so I'm going to play something that might be a little bit more apropos to where we are, the current state. So we might liken it more to beginning stages of flight. We tried to develop planes that paddled air like boats. Or we developed wing-like bird structures that, as you can see, probably didn't work. I think they're pretty cool, though. Or the helicopter, actually, they kept going, but that one wouldn't have been a fun one to be on. And when all's failed, add a bigger engine and a bigger, propeller on it, and maybe it'll go. But as things got closer and closer to actually succeeding, they learned from it, but they learned some things too. You must be able to control the plane. And finally, the Wright brothers were the ones who really got it together, and they were able to succeed. So one of the things that they did really well is they created scientific instrumentation. And this is like the wind tunnel and the lift balance, which actually helped them develop the technology. And they also were able to build models and implement methods of control that help them succeed. And we can liken this a lot to what we are doing right now in clinical neuroscience. We don't really have the knowledge. We don't know the mechanisms of action right now. We have to start with very base principles and build up from there. And so our idea is, right now, we are mostly dependent by doing devices when the patient's in the OR or EMU. And our idea is to take that device, shrink it, and put it in the body so we have an implantable device. And that way we can have much more flexibility to get data when the patient's ambulatory or at home even. We don't have to have leads coming out of the body, which is not a fun thing. And the patient can be in a normal state. But one of the things that is probably the hardest thing to overcome for us in industry is that things like this are new. They're not necessarily something that marketing is able to say, oh yeah, you're going to use this. But we don't have the theories or the practical science right now to say, this is how we're going to use these new signals and these new ideas. So state of the art right now, and the UW site
The
here is
majority
very
of
familiar
patients
with
with
this.
essential tremor
You can
treated
turn
with
off the sound. Thank you. Is showing an essential tremor patient implanted with DBS device and showing the left side with the device off and the right side with the device on and showing the remarkable difference. And that's immediate. As soon as you turn the device on, the patient stops the tremor. And so the device looks like this when it's implanted. It's implanted in the chest like a pacemaker, and a lot of people call it a pacemaker for the brain sometimes. And it has a battery, and a lot of doctors like to call the device the battery. That always kind of gets me because I work on the software inside the device. It's more than that. It's more than a battery. It does have electronics. It has software. So it's not a battery. But anyway, it's pretty fun to mention that to them. But you can see the electrodes coming up, and usually they wrap to the top of the skull, and then there's burr holes drilled, and the leads are implanted into the depth in sections of the brain, or they might be cortical strips, and that's what's happening with some of the patients here at UW. But one of the things that is limiting right now, until these studies are actually happening, is that we are limited right now for approved therapy for stimulation only. We don't have approved closed loop right now. And we still don't know the mechanism of actions, and we have sites all over that are trying to understand what these mechanisms of action are. So here's our world, our universe, and we have our patient, and we have the material interfaces up here, which are very important, connecting the tissue to our electronics. So we have sensors which can be inside the device, or they can actually be externalized. And we are able to get information out of the device via wireless telemetry. And we have our electronics, which obviously are inside there. We also can take that information from our sensors, develop classifiers and control policies, and with other data that we've collected from other patients or other sites, we can actually develop algorithms based on that data. And then we want to be able to do something about it, so we have to get back and control the stimulation in this case right now, but in the future, maybe we could have chemical or optogenetics type, or I don't know what the audio one is. I guess that's a music reference, but basically have some way to control back, add this stimulation back to the body. So anybody recognize this image, where it might be from? Probably not old enough. I did watch this movie when I was in junior high, so this really dates me. But it was a movie called Fantastic Voyage from 1966. And I saw the picture, and I remember the image of the ship, but I didn't remember anything about it. So I looked it up and found out that Raquel Welch was in the movie. Maybe that's why I kind of remembered it, but I don't know. But anyway, this is a story about a brilliant scientist who develops a shrinking ray machine. And he's struck, I think he's either injured or struck down with a terminal brain injury. And this shrinking ray machine, whatever, is used to shrink a submarine, in this case, down to a miniature size, and they inject it into his body, and the crew has to fight all the immune system and all these other things to get to the brain clot, I think it was, and save the scientists. And I think Tim likes this because I think he thinks he's the brilliant scientist. I think we might need to save him someday. Maybe that's what he's thinking. So, but anyway, what we have in our device is we build our devices and this implantable instrumentation based on the existing neurostimulator. And this was an approved DBS product called Activa PC. So it consisted of a micro telemetry and power management and a stimulation engine. So basically 3 integrated circuits plus a lot of outside circuitry to make sure everything is talking and connected to the outside world. And what we did is we added a second processor, and in that processor is the software, the firmware that I worked on for classifying and control policy. We have a hardware ADD converter and real-time telemetry control, or actually signals we're able to send out, either record them from the brain or we can actually stream them out real time. And note that these are connected directly. We can sense off of any of the stim channels with the inputs over here, and we can multiplex those, and we can sense 2 contacts per hemisphere. And usually these are implanted in 2 different hemispheres, or in the UW experience, one is on the cortical and one is in the depth electrodes. And basically, we also would like to, in the future, maybe have other types of sensors that we could add to this too. But the idea is that in the future, we'll be able to have this in every device that we sell. And any patient who has a device like this could be considered part of a research study to develop new algorithms, new control policies, et cetera. And hopefully, we'd like to be able to use closed-loop control to make the therapy better in the future as well. So the idea is, like the Fantastic Voyage, we want to shrink it and get it inside, get this whole payload in there. So we're going to focus a little bit first on a couple different areas, the brain-machine interface and the sensors and actuation. So that's basically pretty low-level kind of interaction with the components. And what we're showing here is a method we're using the Activa PCS at Stanford with Parkinson's patients. What they're doing is taking the Activa PCS, recording LFP data, and at the same time, they're externally connected to, I think they have EMG, accelerometers, and synchronized video. So the key to this is synchronizing these external sensors along with the internal signals from the brain. And this actually wasn't performed, or didn't appear like this. We did post-processing. We got the recording, synced it up with the other signals, and displayed that. And I'll show you what that looks like. So the accelerometer channel is in green. Right below that is the LFP data, and the chart down below is the spectrogram of the LFP data. Now, the patient during this part of the study is off medication, stimulation is off, and he's told to do hand-waving motion as fast as he can. And note, in this case, there's a very strong beta signal in the 20 hertz range that goes throughout this recording. And now we're going to repeat the same experiment, this time with stimulation on. And I'll play that. So the stimulation is turned on about 5 seconds into the recording. You'll see a line of stimulation coming on there at the top. It's 148 stimulation. But now one thing that's very important to note is that the beta signal is basically not present, and the patient is able to move the hand much more freely. So with this synchronized data, they can actually see the effect with the stimulation and how it affects their movement. So here's a series of titration experiments also done at Stanford that show a series of stimulation amplitudes. So first, I'll just start from the very beginning here. Here's the baseline. We have high beta signals right here. This is kind of the rest beta level. we turn on a low frequency stim pulse for a short time. And at the same time, in the video, they also do an audible sound to synchronize on the video. Plus, on the EMG, it also picks up in that signal too. And then before the stimulation is turned on, there's nothing that's changed yet until they actually turn on a 1 volt amplitude. And you see the stim artifact on. And you actually can see a slight, maybe, improvement. Sorry. What happened there? I held the button too long, I guess. Sorry. Slight improvement in the beta. And in between, the beta almost goes back to its pre-resting state. Next time we're at 2 volts, the beta goes down even more. And also up in here, you might see a little bit of gamma indicated. And then finally, when they get to therapeutic levels, because they actually have the patient, doing some, I don't know if they're doing an iPad test where they actually are tapping, but they are basically trying to show their motor improvements. This time, the beta is almost completely gone, and the gamma is also present, which we've seen may correlate. If you have too high a gamma, you could actually have dyskinesias appear. And then there's actually, this is showing when they went 1, 2, 3, 0, they will randomize those stim patterns. This happened to be where it would look like it's incremental, but it just happened to be in one trial where they do that. They didn't want the patient to get used to, an increased therapy dosage, and so this one just happened to be that. So actually 0 is one of them. They'll say stim is on. It might be 1 volt, 2 volt, 3 volt, 0 volt. They don't know, so they're not trying to bias the patient. And one of the things that we have to consider in this system is that we have to be able to sense these very small signals, sometimes less than 1 microvolt, and these are like 3 volts. So we have 120 dB of signal difference. And we make sure that the signals are not getting saturated. Like in this case, we just turned on and we saw, oh, it went away. If we can saturate the signals if we get that too high. The patient probably would complain as well. But we could actually make these signals disappear if we turn the stimulation, like say, to 5 volts or something. But it's key that we get synchronization across all the channels. And the clinician can be observing or having the video and make sure that things are correlating with what they're seeing. Here's another site, the Mayo Clinic in Minnesota, very close for us. And this is an epilepsy study where they actually are trying a new target. This is off-label. This is not approved. And they're trying a new target, and they're actually, to see how, if they've hit the target they're interested in, they're doing a evoked potential using the stim on the electrode that, I'll go to this one right here, it's being stimmed on here and then measured. It's very hard to see that gray, but that's the other lead in the hippocampal region. And this shows stimming on contact 1, 2, 3, or 4 in the AN, and then seeing what it actually responds to in the hippocampal region. And there's a paper on this that describes how they did that. But we feel this is very promising because now it proves that they're in the target of interest, and they actually picked contact 1 in this case. They saw that was the best response, so they knew that they were in the right region. So let's look at another area, and this is interactive feedback. So we're going to add that one up there. And this is at UCSF. This is a very interesting data set, and I happened to be in with the patient when this happened, when they recorded this. And at the time, we didn't really understand what we were seeing until we looked at the data later. And this patient starts out with medication off, and in this case, sorry, wrong button. we have, similar to what we talked about before, we have a depth electrode and a cortical. So we have the cortical signals up on top and the subcortical signals down here. So let's first look at the motor cortex. And the patient comes in and they are kind of off their medication, but not quite all the way off. And the signal is the bottom one here, which is pretty flat and uneventful. Slight beta signal, no gamma signal. But then they take medication. They actually do a test, and they walk, and they still have no dyskinesia. But then they take their meds, and this is a really fast-acting medication for Parkinson's because the patient has severe dystonia symptoms, which is very horrible to watch. And so they wanted to give the patient a little bit more movement. And so they actually give the medication. But then what happened is now that medication spiked and blew up the, sorry. I was trying to show you that the beta went up and that the gamma, it went up and down in frequency, and the gamma went up. And at the end, when that fast-acting medication wore off, those signals started going back down again. The beta started going back down, and the gamma started going down as well. Not as much as the beta did. And then down, same in the depth lead, they also see a dramatic difference between off medication and on medication. And so this was very eye-opening for them, and for us, we were saying, wow, this is really showing some cool stuff. So now let's talk a little bit about adding classifiers and control policies. And one of the challenges with that is, with an embedded system, if you don't have the right algorithm, and sometimes the algorithms might be fairly complex, it's hard to embed that. So what a lot of the sites are doing is actually they're developing algorithms with computer in the loop. So we're streaming data, and we get the brain signal. We run it into a classifier. This is on an external computer that the researchers got their algorithm running, doing the filtering, doing whatever they need to do, and maybe marrying other externalized signals like we showed in the Stanford case, and developing control policies here, and then sending commands back to the device via telemetry and sending stimulation back to the brain. And sites are doing that right now. We're starting, for different types of diseases, different phenotypes. And it's very exciting to see this now because things are working. It's very cool. But one of the things that the FDA is especially concerned about is, okay, you got this, let's say we were to embed an algorithm into a device, what controls, what safety things do you have to prevent that control algorithm running amok? And what we want to do is we want to make the stimulation control work within the range of what a clinician would allow the patient to change. Typically, a DBS patient may be given a DBS activator to control their amplitude based on their symptoms. And the clinician sets the high and low values of that to make sure that they're in a safe range. And the same thing we'd want to do, we want to make sure we're in the safe operating ranges that the clinician defines. And if for some reason the closed loop algorithm got out of control, the patient could always revert back to a known state, or and that might be off, or it might be a safe state that we know is conducive to the patient. And basically that's one of the things that the FDA really likes to see and hear, that we have that safety built in. So this is an example from Peter Brown at Oxford. This was done in the OR, I believe, with externalized leads, but it's the same concept where taking signals and doing a computer in the closed loop, doing the quantification of the classification, doing a control policy, and then sending activation commands back to the device. And in this case, it was a simple check for presence of beta and turn on stimulation. If beta is not present, turn off stimulation. And what he was seeing in the paper, you can look at that, is that it happens fairly rapidly. And the stimulation is not on very often, actually. It's only on when the beta is present. And here's a kind of a picture of what this is the next algorithm that they worked on. The first one was simply beta present, turn stim on, beta not present, turn stim off. This one was doing a more sophisticated phase amplitude coupling with the tremor frequency of the patient and timing the stim pulses to the tremor. And this little graph down below is trying to show that eventually the phases lock up. And what they found is that with his particular setup, a 240 hertz phase difference was optimal for the best benefit for this patient. These are actually maybe multiple patients, I don't remember. But so they tried this, and they tried it a few different times, and it takes like 5 seconds for it to kind of lock in. But eventually it does get a pretty good benefit. And they compared that to normal stim, which is continuously stimulating at 130 hertz. They get really good suppressed tremor. And with the closed loop, they don't get quite as good, but you're only stimulating an average of the tremor frequency. And so it's a big improvement on power efficiency. So if this is successful, and we could implement that in an embedded system, this could really be a big change for the therapy efficiency. And I think if it was embedded, we had the technology to do that, it would probably be more accurate because you don't have to deal with external latencies, which we deal with all the time. This is another UCSF. They're doing a similar type computer in the closed loop. And actually, this one they are doing, I think they might even be starting to do this embedded too, but they're actually looking at the gamma signal and seeing when they have presence of both medication and stimulation, because most patients, Parkinson's patients, usually do not go off their meds completely. They reduce them greatly, but if you have spikes in high medication with a combination of stimulation therapy, you can get dyskinesias. And so what they were looking at was watching the gamma frequencies, and when it gets above a threshold, decrement the stimulation, and when it's below, we start incrementing it again. So it's a gamma thermostat. And we get close home here with UW and also the University of Florida doing similar studies on essential tremor patients. And this shows UF data where they're actually cueing the patient to do a hand movement so that it's hard to see, but there's little yellow bands in front of these green bands. That's their cue. And we are recording data in the VIM, and they're doing both left and right hands randomly and seeing a very good correlation in a decrease in the beta when they're performing the task. And UW is actually looking at this precursor maybe and trying to see if they can anticipate movement. And so they are actually trying a closed loop version of this, and they are doing recordings right now and trying that, and I think things are working well. Same with UW. So one of the last things we're going to talk about here is when we're talking about across multiple sites, multiple different disease states, we're looking at the data that we get from these sites and trying to figure out, are there commonalities? Are there differences between phenotypes, between different disease types? And as we get more and more data, we are seeing some trends. And this is showing, on the left side, it's showing data from Stanford between different types of phenotypes of Parkinson's disease patients. They have the ekinetic and rigid patient, which do not have tremor. And these are the tremor-dominant patients. And I didn't know that before we started these studies, that Parkinson's could have tremor, can have akinetic, and it can have even dementia-like symptoms for a lot of these patients. And so what they're looking at is how does it compare across patient populations. I think this might be 20 patients total. I don't know what the breakdown is between the two here. How many of each, but I think they have 20 patients now with this implant. And over on the right side, we're looking at data between patients that have OCD and Parkinson's disease, and you see quite a different signature. And they're looking at that and just seeing kind of interestingly to see what's different. And so ideally, in the future, we would have large data sets that could help us define therapy levels and maybe the best treatment options for patients based on data that they could compare to other data sets, find a match, and see, okay, this is how we're going to treat this because it's very similar to X. And then be able to put a program into the device with the right algorithm and then do a nice match. That's in the future. Not there yet. And so one thing that we've done internally as we collect more and more of this data, one of the biggest time spent activities with Parkinson's patients or any of these movement disorder patients is setting up the correct contact locations and also the right amplitudes. This one was just looking at the contacts that were picked. And what we did is we analyzed data from 15 Parkinson's patients and tried to develop a SVM learning algorithm to decide what would be the best contacts to pick for therapy. And the truth would be whatever was programmed. We didn't know what they actually picked when we ran the algorithm. We knew that there was going to be a selection, and it might have changed actually over the period of time that the patient sees them. And sometimes they dial in the therapy over months, and it's a very hard thing to do. And so what they tried to do with this is see if they could do an algorithm approach to decide which therapy would be the most therapeutic. And the truth was, as I mentioned, matching what the clinician picked. And it was interesting. They found that the best frequencies to look at were the low beta frequency and a very low, even lower, I think it was in the 3 hertz range. Those two signals of at least the 15 patients that we looked at with this data set, those were the most influential on deciding which contact pairs to program on. And we ended up seeing that we got a 95% accurate. So out of 83 attempts, because they are multiple sessions where the clinician may adjust the therapy, we had 3 errors out of 83 attempts. So it's promising, and something we will consider in the future, developing more. So kind of in summary, we have all these things around us. I guess, sorry, I have one more. Not in summary yet. We have one thing that I have to make sure that you realize that none of this is on label. using MRI or fMRI with DBS is not on label. But that's something that we know we're limited by using the DBS electrodes. We only have right now currently 4 electrodes per side of a device. That gives you a very limited space that you can look at inside the brain. We need to understand, what's going on because of therapy, what's changing when we do apply stimulation. Now, this is not recommended, and I have to put that in red so we know that we are not promoting this at all. But it's something that we have to get more knowledge on, and listening to a lot of the talks today, maybe if there's models or other things that we can do to help learn, what areas of the brain are being affected, that would really make a huge impact on the therapy. So now, in summary, we looked at all these different kind of areas. We talked about sensors, we talked about classifiers and circuitry, big data, modeling, and actuation. And as we look at this, we have this scientific package trying to embed that in the body. And we have this electronic circuitry that we hope will help aid in that and give us more information. We may not be able to do it all from within inside the body, or maybe intra-body if we have multiple sensors. Maybe we can have intra-body types of communication with built-in accelerometers or implanted accelerometries maybe in the future or something. But we need that probe, and we need to help these patients. So one last thing I'll leave you with is, this is in a New York Times article, fall 1903. They were saying that flight probably won't ever happen, maybe not in a million years. And as you all know, 2 months later and 8 days later, the Wright brothers did fly. And so don't give up hope. We're working on things, but we have to take them as we can get to them. And thank you very much for your time.
Thank you very much, David. Just for a little bit of context, all of these studies you saw are university industry collaborations where the university investigators, both engineers and clinicians, are building on the hardware platform and the tremendous knowledge base that you have provided and coming up with their own models for control paradigms and clinical investigations. And then the FDA allows this investigational device exemption to have these devices that are not yet approved implanted into patients. So one quick question while you are all thinking of questions. Okay. So there are now on the order of 100,000 DBS units that are implanted in patients over the world. As you move over to this new platform, you're going to generate and collect a huge amount of data. Can these algorithms for control be drawing from data from all of those patients, or are you only going to learn from the one patient who has the device? Related, can the device be intelligently adapting its algorithm? Is the FDA okay with that?
Well, I think to start with, we would do probably on a single patient, much like we're doing right now, and it'll be more prescriptive for that patient. But over time, like you say, as we gather more and more data, we can start seeing trends, and we'd have to do a clinical study. With the FDA, you basically have to do a study every time you want to say that, okay, there's a common theme here. How is it going to help the patient? Is it safe? And if it is, and we can prove that in a clinical study, then maybe we could actually have more of a, pie in the sky where we have the algorithm across many patient population and be able to derive decisions for control policy and algorithms.
That's one of the challenges is that the technology evolves much faster than you can do the clinical trials to get approval. Question in the back here.
We do have 1 or 2 sites that are studying OCD, and we also have a depression study going on as well. And they're radically different between essential tremor, probably one of the easier ones to really see what's going on with your therapy control, compared to like depression, which may take weeks to months for that effect of the therapy to happen. And so it's a huge challenge, with the different disease states like that. Does that answer your question?
There have been a number of clinical studies looking at DBS and other technologies for depression and other psychiatric diseases. There's a DARPA program, Subnets, that is focused on exactly that area. Other questions?
Yes, I've got one here. Obviously, the algorithms that do the closed-loop simulation, they have to be very efficient and quick. I'm wondering if you can speak of how much leeway you have in terms of the timing for the decision-making, such that the stimulus still does something.
Yeah, and it really depends on what kind of algorithm like that. The phase-coupled one, if you have 5 Hertz signals, what's that, 200 milliseconds, right? You have to be, maybe you're not going to deliver the stimulation on that period, but you're going to deliver it on the next period, but try to make it accurate within that next period. And so that's what I deal with all the time, is trying to figure out, is this even doable? Especially externalized, you have a lot higher latency with the round trip, we call it. So the signal coming in, acting on the algorithm, sending the command back down, and then actually activating. When you have computer in the loop, that's a huge problem. Now, when we get embedded algorithms and we have either specialized hardware and enough horsepower, like you're saying, inside the device, then it becomes a lot more manageable. Then we can probably get down, in the sub 25, 30 milliseconds based on, if you have high power processors. We're not there yet. I mean, that's my goal. I want to make sure we get modern processors with DSP technology and point-to-point processing for the future.
In the back.
It's a race.
Hey, thank you for the talk. I have a pretty basic understanding of everything you just went over, and I was just more curious about why beta frequencies, I think it was, are so problematic, and what about them? Are they like just a red flag, or is it beta waves themselves that cause a problem?
I don't think it's the problem. It's probably the symptom, and there's probably more information in that beta frequency. We're just looking at just the presence of the beta. There are also people looking at information encoded in the beta, between higher and lower frequencies. I think that was mentioned in some other talks too, where there's, what's the word I'm looking for, but pairings between, higher frequency and phase amplitude of the beta, and maybe there's higher frequencies riding on that beta. So beta might be the carrier. And maybe that's, there's lots of theories on this. Nobody really knows for sure. It could be, some people think, well, beta is a blocker, and it actually inhibits movement. But there's many theories, and I don't think any of them have been fully disproved or decided that that's the truth. So if anybody wants to work on stuff, that's some fun stuff to work on, I'd say, and we need a lot of help.
I was curious, given that executive function is a significant predictor of quality of life for both patients and caregivers, is there anybody that you know of that's trying to account for this and sort of working on these algorithms?
Yeah, that's part of, when clinicians see their patients for follow-ups, they ask them about, they do standard scoring for like Parkinson's patients, their quality of life metrics, and I think they have actually counselors that work with them too and worry about, because the poster that was here yesterday talked about, the changes that can happen with therapy like DBS. It can affect their personality sometimes. It can affect the caregivers sometimes because they were dependent on giving this person there, or the person was totally dependent on them, and now all of a sudden they're not dependent on them, and they feel a loss. So there's dynamics with both in the family and also in the patient themselves. So I think that's, especially in the psych cases and the OCD, that's a huge issue, of course, because they are based on that, premise. So there's a lot of counseling that needs to happen on some of these patients as they get changes in their state of the disease.
Let's thank Dr. Linde again, and feel free to come down. We have a break coming up.
Ask those guys.